everybody. Today we'll be solving a rolling motion problem. I hope you are all familiar with rolling motion. If not, I'm gonna put a link to the video where I discussed rolling motion. So if you have no idea what rolling motion is, I strongly suggest that you go and watch that video first. So anyway, we are gonna starting our problem. So initially we have a system which is at rest. It has a cross-sectional area with radius r. I don't know what it is. It may be a sphere, it may be a disc, okay, hoop. So I don't know what it is. I don't care what it is, okay. But it has a moment of inertia with respect to the center of mass. Let's call it I. Initially it's at rest, and then there is an external force being applied on the system like that, okay, at this point. And then the system rolls without slipping. Okay, so the system rolls without slipping. I hope we all know what it means. So the question is, what is the change in the total mechanical energy of the system as it travels a distance d to the right? Okay, so I'm calling this distance like my positive x direction. Okay, so I want to get my answer in terms of F and d. F is the magnitude of this force and d is the distance traveled. Okay, any ideas what the answer could be, okay, without solving the problem? Okay, just think about it. What can be the answer? Okay, any ideas? How about if I say F times D? Could it be the answer? Why? Because work done by this force could be, right, F times D. And if this is the work done by this force, right, and this is the only force doing work here, I think, right, we will also discuss that, then this should be equal to delta E due to the work energy theorem, because this is a non-conservative force, right? The work done by a non-conservative force is equal to change in the total mechanical energy of the system. So this is a big question mark, okay? So if there is a rolling motion, you should always ask yourself, okay, whether the work done by a given force is really F times D. So today I'm going to show you that the work done by this force is not equal to F times D. So all excited? So we're all excited? So F times D is not the work done by this force. Just think about it, ask yourselves why, and the answer is coming shortly. Okay, so let's start solving this problem. We will first show all the forces acting on the system. First of all, we have mg, right? And we have a normal force, just like that. There is an external force like that. What else? Well, there is friction, right? We discussed that before. So since this is rolling without slipping, okay, there has to be a static friction. So what is the direction of friction force? We don't know, okay? We're just going to make an assumption. We can say the friction force is going to be in that direction. Why static? This is static friction because the point of contact here is not moving with respect to the floor. So two surfaces are in contact with each other and they're not moving with respect to each other. So we have to have F static. Good. So now let's write down the torque equation. So this system rotates like that, right? So at any given time t, my omega is going to be like this. So I'm going to choose this direction to be my positive direction. And meanwhile, it's also moving to the right. So I already chose x to be my positive direction to the right. So now the torque equation, let's call it rotation. So I'm going to be looking at the rotation first. So the torque due to F about the center of mass is simply equal to R times F. And there is Fs here, minus R Fs. This should be equal to torque I times alpha. This is good. So I can simplify it a little bit. So F minus Fs must be equal to I over R times alpha. Good. How about the translation? Well, I have F and Fs pointing in the same direction. F plus Fs must be equal to mass times acceleration. This is good. So I have these two equations, right? Okay, what else I can do here? Rolling without slipping, right? Rolling without slipping. Then we can simply say that alpha is equal to A over R. So this is my condition for rolling without slipping. Okay, wherever I see alpha, then I can put A over R. Okay. So let me write down the equations one more time. F minus Fs is simply equal to I over now R squared times A. So I'm going to write everything in terms of A. And I already have F plus Fs is equal to mass times acceleration. This is good. So at this point, what we can do is, I don't know what Fs is, so it is maybe a good idea to eliminate it in my equations so that I can solve for A in terms of F. So the main trick is you add them side by side. So you'll have 2F is equal to I over R squared plus M times A. So I know what A is in terms of F. This is good. So now I can find V. So V squared minus V initial squared is one of the kinematics equations. I hope you all remember that. So 2 times A times D, right? This is my displacement. So initial velocity is 0, so I can put 0 here. So my V squared is simply equal to that. Okay, this is good. And here my A is equal to 2F over this term here. So I can equate the denominators here. I'll get I plus mr squared. And I'll have 1r squared down here, so it's going to be r squared like that. Okay, so this is my A. This is good. So now let's write down the energy. Okay, in my previous calculation, I found V squared as 2 times A times D, where A turned out to be 2FR squared over I plus MR squared. Good. So now we are going to write delta E. So in my final state, the final energy, is final minus initial, right? So in my final state, I have rotation and translation. Okay. So I have 1/2 mv squared plus 1/2 I omega squared. So since this is rolling motion without slipping, I know that V is equal to R times omega. So since I don't have omega here, I'm going to write everything in terms of V. So wherever I see omega, I'm going to write V over R. Okay? So this just gives me V squared over R squared. It's good. So if I use the common parentheses, by the way, initial energy is 0. So I just put 0 here. So 1/2, this gives me M plus I over R squared times V squared. Okay? So V squared is nothing but 2 times A times D. I already found that. So I'm going to equate the denominators here. So this gives me mr squared plus I. This is good. So instead of A, I'm going to put that. So there's 2D. A is equal to 2F R squared over, say, mr squared plus I, right? Good. Here is the magic. Are you ready for the magic? All ready? Okay. You see, this one and this one goes away. They go away. R squared cancels this R squared. Okay. This 2 cancels this 2. What is delta E? 2FD. Where does this 2 come from? Okay. So I was expecting the change in the total mechanical energy would be F times D, but not 2 times FD. So is there something wrong here? That's the question, right? So why is it 2 times F times D? but not F times D. Okay, so the answer is all about the definition of power and how this force is acting on the system. So as you may recall from our rolling motion chapter or discussion, what we said was for the rolling motion without slipping, at any given time t, okay, this point here, the point at the top here, will have some speed, which is going to be twice as much as the center of mass speed, right? And the force is actually acting right here. So work done by this force is actually can be calculated using the definition of power. So what is power? F dotted with V, right? Velocity. So since they are parallel, the dot product just gives you F times V, which is F times 2F times V center of mass. Okay, so this is time dependent. V center of mass is time dependent. So in order to be able to find the work done by this force, we need to take the integral, right? So 2F is constant. So this is V center of mass times dt. 0 to any time t, so it's t prime. So this is nothing but V dt integral. This gives us the displacement, d, right? So that's why the work done by this force is actually 2Fd. Okay? Let's look at the other forces. So there is mg pointing like that. There is normal force like that. So since they are perpendicular to the direction of motion, so there is V center of mass here. So the power due to mg is equal to 0. So this is 90 degrees. So the power due to the normal force is acting at the point of contact. So let's recall, for rolling motion without slipping, the point of contact is at rest, right? So the velocity here is 0. So the power due to F normal would be 0. Due to same reasoning, so there is static friction force. So the power delivered by the static friction is also 0, because the velocity at this point is 0. So the only force that does work here is this external force F, and the work done by that force is just 2Fd, and it accounts for the change in the total mechanical energy of the system, which is also equal to 2Fd. I hope it's now clear, and I hope you also enjoyed the video, the solution. I'll try to solve more rolling motion problems, and I'll try to include the concept of energy as well. I look forward to seeing you soon in other videos. Take care of yourselves, study well, and always be happy. See you later, guys. Bye.